Okay, this is a video about how to implement the direct analysis method using Staad Pro. Latest edition or current edition that I have is the Connect edition. I'm going to start off by actually opening up a model that I've already completed. Just taking a quick look at these settings in the model. So here I've created a model with 3 portal frames. The model is based on the learning module number 9 that is provided by Staad, which is a great tool that I use in order to just have a general understanding of second order effects and structures. So I've created this model right here, like I said, based on that module. And each one of these settings has a different set of loads. Each one of these models rather has a different set of loads that are on it. So let's just get a feel for first, I guess, the graphical user interface, because it's slightly different than previous versions of Staad. We have, of course, the ribbon tab, which is, you have the file information. Everything is self-explanatory. I've accidentally closed out the model. Let's get back into it. All right, so we have the file, geometry tab, which of course allows you to lay out the structure. View tab, which gives you different perspectives in your input and output views that you want to take a look at. Selection tab, which is self-explanatory, allows you to select different things. We'll get into it a little bit more in detail. Specification tab, which allows you to provide certain properties to the structure. Everything related from essentially your releases to any type of reduction that you might want to have in the element. The supports, let's go to the loading tab. So in the loading tab, we're able to obviously insert different loads based on the load cases that are defined here. Here in this model, we have a couple load cases, 3 load cases actually. The Q sub U load is the vertical load that's on the structure, and it's shown as 130 kips. And you can see that it's quite long. So if I wanted to adjust this a little bit in terms of what I'm looking at, I can right click and go to structural diagram. I'll go to, let's investigate under loads first. Scale, it makes more sense, right? So I'll take the scale, and these are vertical loads. And so right now, I'm just going to kind of, I guess, do some things to see whether or not that'll instantly reduce it. Well, you can see if I increase it, that I end up having too much. So I need to graphically show this. So put it at 1. That's a better representation of what I want to look at, what I want to view. All right, next tab is the Analysis and Design tab. Here you will specify what type of analysis to perform on the structure. You will put in the parameters that's required in order to design the structure under the design tab, even though it's not a separate one, but now you would have to click right here, kind of like these sub tabs here. So we would put in these parameters. So the next set of, I guess, aspects of it. There's this workflow kind of like menu on your left hand side. Tells you what part of the workflow you're currently in. This is pretty new to Staad, or at least it's new to me. Excuse me. And here, basically, the two important things to focus on would probably be analytical modeling and post-processing. Here it's telling me that I cannot get into post-processing, essentially because my analysis has not been executed. So this workflow requires the results of the analysis, but currently these are not available. Please run the analysis first. I'll do that at a later date. Go back to my analytical modeling. And you can see here under this geometry location, we have our nodes for our structure. As I select a node on the table, on the list of tables, different nodes will highlight down below. They will highlight on the graphical user interface. So talk about the graphical user interface. Obviously, this is the main view window, model view window that we have that provides you a representation of what you're viewing. Let's see here. I think we might be able to change some displays of the structure. We'll leave it at stick right now, but you can see, we could do 3D rendering, pop up what the structure actually would look like in 3 dimensions. And it's taking a little bit longer than what I would expect it to take. So we're just going to skip that step right now. I believe I can kind of show a little bit of what that looks like, through my, again, structural diagrams, and let's just say I do a full section, 3D section, say apply. Take a look at what I'm dealing with here. My view, can rotate this various axis. I'm not doing this dynamically because I either don't know how to do it dynamically, or I don't think Staad actually has that feature, which kind of sucks, but that's okay. Either which way, you can see that, I've oriented my weak axis of my columns, in the X, such that the structure is going to be bending about the weak axis in the X and Y plane. So the weak axis is, or the webs of the column are running parallel to Z axis here, and the beam is bending about a strong axis for any vertical load that's placed on the top of the beam. Let's see, like I said, I could rotate this thing. It's kind of whack, but nonetheless, we have a way to view the structure in 3D. Okay, let me get back to stick view real quick. Go back to my structural diagram. There's a button for this thing too, but because I am basically getting familiar with this particular interface, and I haven't used Staad in a long time, or at least I use it in and out. So this takes me a while to find basically where they move my cheese to. All right. Anyway, so the other thing about the geometry tab, obviously, I could highlight, the elements. They label all these elements as beam elements because that's the type of finite element they use, I suppose. Um, and so rather than columns or other type of members or beams, braces, they would all be labeled in here under the beam column. Okay, so let's take another look at it. You can see right here, we have for beams, W24 by 76. We have for columns, W12 by 58. One thing to note about this analysis for this frame, here's my 0, 0 at this location right here. And, this first frame is a portal frame that's braced out of plane. So we're doing two-dimensional analysis. And it's fixed at the top, pinned at the bottom. And we modeled this with the actual uh, displacement that's allowed by the erection tolerance, which is L over 500. So here you can see that the units are in inches. And so if I go to joint 2, which is at the top left corner here, that in the Y direction I have 144 inches, which is 12 feet. And if you take 144 and you divide that by 500, you will find that that value is equal to 0.288. So this is about a little bit over a quarter of an inch in terms of the displacement over 12 feet. And that's what's allowed by the Code of Standard Practice in terms of erection tolerance. So these nodes are, modeled such that the structure is actually in its kind of skewed position. And that's what the first model is about. Let's see, the second one is also similar to that, but it has different loading. Okay, so this second one is the same thing, but with a different set of loads. Now, go ahead and show you what those loads are right now. Again, on the first one, I have 130 kips vertical. And I just focus on vertical loads for now. On the one in the middle, I have 110 kips. Let's just go ahead and show this thing in the X and Y plane. So I have 110 kips, and then again on 130 kips on the third frame, and that is placed in combination with a lateral load. But we'll go frame by frame. So on the first one, I have I have 13 kips, 10% of the vertical acting on it in its displaced configuration. Same deal for the middle one. In this case, it's 11 kips. And I'll throw this in 3D so you can see it a little bit better. The load highlights as you select it. And then at the last frame, I have the same amount of vertical load as the first one. However, I have 13.78 kips on the last frame, because in this case I am basically adding a little bit more notional load to account for the imperfection and also the stiffness in this case, a total of 0.3, so 0.003 rather, should I say, uh, which is 0.3%. Now the notional load can be increased to account for imperfections by 0.2% of the vertical if you don't model the imperfection. If you know model the column as straight as nominal as we would normally do in our analysis, certainly as we would draw it on our drawings. So we would have everything shown as perfectly plumb and square to one another, whereas in reality the structure is not constructed that way due to the allowable tolerances that are specified in the code. Well, to account for that in your analysis, you have to put a little bit more load. So again, 0.2% additional load, 0.2% of the vertical load, additional load added for that reason. And then if you want to, also not worry about the stiffness reduction, your tau sub b aspect, you can add another 0.1%. So the total of the two would be 0.3%. And as I said, it's 130 load, 130 kips on that frame. So multiply that by 0.003. And you would get 0.39. Multiply that by 2 to account for two loads. You have 0.78, and you add that to a 10% lateral load that is just part of this example to begin with, and you have 13.78. That's where we get that number from. All right, now in the direct analysis method, of course, when we're trying to capture second order effects in the structure, we have to run a second order linear elastic analysis. And in order to do that correctly, you need to analyze the structure with all of the loads acting on it, essentially, the vertical combined with the lateral and any other load that you would have. So the way Staad addresses that in terms of the analysis is by creating a so-called repeat load combination. And so this load case, it would show that you have both vertical and lateral together. All right, shown here again, it's all scaled up kind of to show you the magnitudes of the force that's acting on the structure. That's why you see these vertical loads is so much higher than what's represented for the lateral loads. And that's how we essentially get the analysis to run. So this repeat loads means essentially that it's a rigorous second order elastic analysis where the structure is analyzed with a small portion of this load first, the results calculated, and then the stiffness matrix is updated based on the forces in the members and the displacement on the structure, and the structure is analyzed again. And this goes on repeatedly until the structure is stabilized and all the load has been placed on the structure. At that point, you will have a analysis that represents the forces acting on the structure in the displaced location and the displaced condition, and the reactions, internal and external, that's required to maintain equilibrium. All right, so that's what that is about. Now, load case definitions. Now, the direct analysis, how do we specify Let me know which loads are, let me know which members are being reduced, and how do we specify the direct analysis definition here? Well, it's two places. So here in the loading, you could start off with this definition of direct analysis, and this is added to the structure. And when you bring in these different parameters, you have to assign a value to it. So a value of 1 for flex essentially is saying that you want to reduce the flexural stiffness of each one of these elements that are listed here on the right hand side by 0.8. Okay, so even though the value is 1, it's either 0 or 1. You click on the help, and then help spell it out for you a little bit, but basically that's what that means. And I'm not going to get into it too much because it's basically going into the weeds, but just understand that's what that means. Now you also have to specify a yield stress for the element, because this is where we would take into account the residual stress, and based on the element itself, we would have to, for the material nonlinearity, you have to specify the yield stress. So it would get reduced, but asking you, well, how do we start? We start on, what's shown as 7,200. This is actually in a value of, I believe, kip feet or something like that, or kips per square inch or something. This is probably in kips per square inch. It's really 50 ksi, but just because the way that this thing is set up, you have this value of 7,200 shown, but it's 50 ksi. Well, I'll show you how that occurs later on. It's just a weird quirk with Staad. Anyway, so axial also says, well, in terms of the other stiffness to be reduced, we have to reduce the axial stiffness as well for all of these members that are part of the lateral force resisting system on which we are conducting the analysis, direct analysis designed for. This is important because you only need to specify it for the members that are part of your lateral system, on which the remainder of the structure depends for their own stability, their lateral stability. And by stability here, I mean, in this case, the ability to maintain its equilibrium, its structural capacity in a deformed shape, and not have extremely large deflections. So that's essentially what we're checking for. We're going to design these columns and these beams for moments and axial forces and shears that are required in order to maintain equilibrium. And that's if this structure is stiff enough just to begin with. Okay, so we have the geometry, we have the loads on the structure, we have the direct analysis definition. Of course, there are other things, simple things like, of course, placing reactions at the base of the structure and stabilizing it. Also, reactions at the top in order so that I could run it in 2D, because this is a 3D analysis, 3D analysis program. Let's see, anything special. Properties, these members, I already said what they are. There you go. You have the shape type. Materials, they're all steel. Click on steel, you'll see everything highlight. Click on concrete, no stainless steel. So this is just the material location right here. Specification. This is if I had any type of special releases on the beam, I would specify it here. If I had any particular behavior where it was either tension only or compression only or behave like a truss, however you want um, specify the material, the behavior of the member. So I have under the release tab, no releases. Nothing has been defined, and when it is defined, it's in it, and it shows up in this little window right here, but it's not. Go into supports. Of course, here I can put in my supports where they're needed. I have my out of plane supports pinning at the top. Take a quick look at that. You can see that I've released any action in the axial direction, X. I've allowed it to move also vertically, Y. I've not allowed it to move in the Z direction, and I've released all the other rotation, all the moment capacities, all the other rotation. Also, you can define springs here if you like to, you wanted to model other degrees of stiffnesses. Once these are infinitely stiff reactions, which uh, is rare, but either way, it's just the way we model it. All right, now in the analysis tab, one will go in here and define a command, for example, and the computer is asking you, well, what kind of analysis do you want me to perform here? And this is where you would say, hey, I want you to perform a direct analysis. So you would click on that tab. There are a number of tabs. The focus here is on direct analysis. It asks what type of design method you're using, LRFD or AISD. This software can do both. This particular program is, this particular module is based on LRFD, so we're using LRFD. Print option, I don't have it printing anything. I could make it print all. In fact, let's just go ahead and do print all, see what happens. For the tolerances and displacement, I don't have any value. Number of iteration, we could put that as something high. This is actually if I wanted to define a command. So I'm not going to define a command, but I would put something in here. Let's say it's 20 or 15 or whatever you want to do. The tolerances, you can also place tolerances and display on tau or the displacement here. We'll get into that on another video. And let's just take a look at what I've actually done. As discussed, I've used 20 iterations, printing all. I don't have anything specified for the tolerances. It's either one or the other, either like the number of the tolerance value or the number of iteration that you would want to specify. This worked for me perfectly fine using 20 iterations instead of displacement tolerances. This area can trip you up a little bit, so you have to be careful about these values. That's it for this. Everything else is grayed out. What's active is just what's shown on the green checkbox, and it's saying that we're going to perform a direct analysis. In the design section, here, this is the location where you would specify checking your member per the code. Okay, so you would have to specify these different parameters, and the code parameters here are things like which design method you're using. I'll just double click on it so you can see, or at least I should be able to see it, but it doesn't work like that with this one apparently. I'm using LRFD as specified before. Now, even though I told it that, I told it I was going to be using LRFD in another location, didn't I? in the analysis location. Well, that's because it's trying to figure out when it runs the analysis on the repeat load, should it multiply the loads by 1.6 and divide it by 1.6 afterwards. Um, and that happens in the analysis. So should it do that or not? Um, that's what's required by AISD. Here, we're using LRFD, it's not required, and that's how you tell the computer, don't do that, essentially, okay? If you use AISD, that's what it would do, and that's a calibration of AISD and LRFD. In the design section, you still have to come back and tell it again, essentially what you're doing, which I think is a little odd, but nonetheless, that's the situation. It's just a legacy, I'm sure, with Staad. So we have these, we code selection, 50 KSI, as I told you, the yield strength, again, I'm specifying it here again in a different location, because I could have all different types of members, and I guess in the design side, you need to specify the yield stress again. This is the ultimate strength and other parameters like the unbraced length or flexural torsional buckling. Even though it's not my situation here, we're only looking at flexural buckling, essentially, but that's fine. Put that in there. Well, I like to just define all of these for each one of them, just to ensure that I have the right length. These are slenderness lengths that are used for slenderness calculations. Again, just to ensure that it's using the correct length. If you subdivide these members, you would need to go back and select these elements that are subdivided and assign it the proper length, because Staad would essentially treat the default length as the node to node distance between the that defines the element. And that's why it's important to go back in here under the design tab and specify what the actual design parameter is. Okay, so this is the unsupported length at the bottom, at the top for the extreme fiber. Let's see here. Again, just unbraced lengths, just making sure that nothing gets tripped up here. I have to get into the details to see whether it's needed or not. Over time, you would have a kind of like a checklist of parameters of what's needed based on steel design or concrete design. Tracking essentially is the level of detail that is provided to you for output, so that you can see what the computer is doing in terms of calculations. And those are the parameters. They all are under parameter 1 folder. Close this folder. I could have a different set of parameters. It would then be parameter 2, etc. Code check is essentially to go in there and tell the computer, I want you to check it. All right. So check the adequacy of members based on specifications of the desired code. And that's that. No additional parameters are needed for this particular setting. All right, and that's it. As I selected, you can see it down here on the bottom. Use my cursor to assign. These are just the mechanics of how to assign that parameter to these elements, but everything is already set. And now that that's completed, you would go under analysis or design, right? Doesn't matter, and just click run the analysis. So I don't like to have errors, obviously, errors of concern, warnings are some things to note. I like to have 0 errors and obviously 0 warnings if possible. So, but some of these warnings are avoidable. Zero errors is absolute requirement. So zero warnings is the other situation, uh, which would be desirable. But here, this warning, we'll read into it. It's not a big deal. We'll read into what that warning is about. Now, under utilities, you can see essentially what's going on with your input file or your output file, and also your analysis logs. And there are other things here like pulling up calculators, etc. So, okay. Now, for analysis output, if we wanted to see what the warning was about, and it's telling me that this structure is disjointed, but I can ignore it because basically it's each portal frame and then this example, so that's not a big deal. Here I have some other messages telling me essentially that just be aware that the moment balance does not consider secondary effects of P delta or direct analysis. You get this message whenever you use second order analysis. All right, and you can step through here and you would see essentially line by line what's going on. It's a bit coded, so you have to be able to understand and read the code values, the syntax that Staad provides you with. If you wanted to check out the design of your memory, you could just click on this section right here. And I know it's very texy, but it's very informative. But you can come in here and see detailed calculations. So we can see that member one here actually has failed. All right. This is just a numerical value. These are the calcs, and it's going to tell you exactly why it's failed, what's going on with the structure. So these are the numbers, right? Same thing for each other, or any other member you want to take a look what works, what doesn't work, right? So close this. Let's see this in the post-processing view, graphical view. So I would select post-processing, and I'm only interested in taking a look at what happens for my load combination that includes vertical and lateral load, which is my repeat load combination. The other two would essentially be the results of the first order linear elastic analysis. So I'm going to kick those out of my available. The other tabs here, I can have ranges of what I want to see, the results, view options, get into setting these different settings so that you can have the structure pop up the way you want it to look. Anyway, so we say okay here and we take a look. What happens is the first thing that it's giving me, it puts me in a displacement view, and it says here on the bottom right that this is load 3 displacement. Gives me a look at what this thing is, and I believe I can hold down the control key and wheel my mouse right up to increase the lateral deflection, down to decrease it. So I go up so I can get a more dramatic feel of what's going on with the structure. See that it's bending in the way that I expect it to be bending. Nothing funny is going on. I put it in 3D, it's not popping out, it's not flopping. So we expect this. Okay, and I can get the displacement at each one of these nodes. So 2 and 3 should have the same thing essentially in the X, right? You will see 2 and 3, essentially that same thing, 5.2, 5.2. 6 and 7, they have less load. So we expect a little bit less deflection. And that's the case here. And then the third frame, 10 and 11, has more deflection. and that's because I have more lateral load on here. And like I said, the structure is different for this one because it's nominal than it is for the other two because they're in their displaced configuration already. They have less lateral load. However, you can see that essentially I've generated a little bit more deflection here, which in theory would also produce a little bit more moment. So that's why you're able to essentially uh, not have to worry about tau sub b or um, the modeling the imperfection as well. Now, let's just get to the nitty gritty of this, and that would be the beam results. That's what we're kind of interested in. All right. So here, what's being shown is as soon as I clicked on it, it's giving me the bending moment diagram, for this load case. Again, it's just in the beam, which is an interesting configuration because this is about the z-axis. But I told you that these are bending about their weak axis. Okay, so I need to know what's going on about essentially the y here for the beam or the x, whichever one they define it as. We'll see. So I will have to right click, go into my structural diagrams and design diagrams. Let's see, loads and results. Let's say I want to look at the moment, right? And I will just click Y here, hit apply. I can change this color to be something that's consistent with the other one. Let's just make it blue because, well, let's make it red to be consistent. Say okay. Again, hold down the control key and wheel up, and I can see the bending moment that is occurring, the bending moment diagram for the columns. And right click and go back to this value right here. I may be able to actually pop in the loads for this case. Let me see here. There may be a way also to show the value for it directly, but we can always look in the table. I'll hit apply. All right, so showing the loads will just give me the external loads that supply. We already know what those are, unless I need to print it out for some reason with that view. I don't need to show that now. Apply. Let's see. So this column, say for example, column 1, which is again noted as beam 1. I can select it and I can find out the forces at that node or the forces at the other node. I could look at it in terms of a summary, and it would show me what are the maximums and what are the minimums. On the envelope, same thing. What controls? So come down here, maximum bending moment. The data is essentially the same here. It's just shown differently. This is for all 3 directions and all 3 rotations versus just focused on bending moments, axial forces, or shear forces. So here I can take a look and see, oh well, what's my maximum? Here I have 1662.5 kips, right? Now let's compare that with number 7, which is supposed to be the one that's more lateral load, nominal analysis, which is an easier one to do, and see if I have more. That's number 7, and yes, I have a little bit more, so I have almost 1700 kip inches in that case. All right.